Okay, so picking up where we left off last time, we did a bunch of stuff about the fundamental theorem of line integrals, closely related idea, path independence, right? And in using the fundamental theorem of line integrals, of course, you need an anti-gradient, right? That's the f, the little f that you plug the endpoints into to compute. So how do we find that? And in the example that I showed you previously, I just pulled it out of thin air, right? And sometimes you can kind of eyeball things and just kind of notice, right? But in general, what's if you have a non-intuitive example, how do you actually go about doing this? So here's the big idea. If you want your vector field to be a gradient, keep in mind that what that means is that the components of your vector field have to be the components of the gradient, of course, right? And that just tells you three equations about what the partial derivatives of this little f must be. So that's the first observation. Second observation is that, well, if the partial derivatives have to be certain things, then that means that f has to be, well, three different partial antiderivatives. Now, again, that's just kind of a grammar thing, P is the x partial of f is morally the same statement as f is an x antipartial of p. Right? Okay, so now here's the problem. This f has to equal to all three of these things at the same time. Wow, what if these three things are different? Does that mean we're dead in the water, right? Are we out of business if that happens? Well, kind of, but you do have to be careful about what you call the anti-partials, right? So you all remember the whole business about plus c from single variable calculus. The big idea of the plus c is that this thing that is your f, its job is for its x partial to be p. Now, this first term handles that, right? But this second term is a recognition that anything else you put in here whose x partial is 0 isn't going to change that fact. Right? So you have to be very careful about this. It's not just a constant any longer that you add in. It's not just a c. Now it's any function of the other variables, any function that does not involve x. Right? So the tricky bit then is f has to simultaneously equal to all three of these things, sure, but you have a lot of flexibility in what these things might be, given these, again, what we call partial constants. Natural terminology, I think. Okay, so let's see an example. How does this actually play out? And here we go. We want to find an anti-gradient for this vector field here. And this vector field has three components. The first component, I need to take the x antipartial of that. The second component, I need to take the y antipartial of that. And the third component, I need to take the z antipartial of that. Now, again, that's just following the formula from the previous page, right here. So easy to do, no problem. These are all polynomials, no sweat, right? And you write this down immediately. But again, don't forget what you've written down here. These are not the antipartials. These are just arbitrary antipartials. Altogether, the antipartials have to include, if you want to talk about all possible antipartials, you have to include the partial constants. So the question is not whether these three things are all equal to each other. They're obviously not. But that's not the question. Right? The question is, can you make appropriate choices of C1, C2, and C3 that'll make these three things all equal to each other? And if so, then F will be whatever those three things are. Okay. All right, so now this is what I like to call kind of a game. It's kind of strategize. How can you make? I need all three of these expressions to be equal. I need to basically any term that shows up in one of these, I need to also be in the other two, so that everything just kind of lines up. Okay, so let's take these one at a time. Now, obviously, there's an x squared y there. There's an x squared y there. There's going to need to be an x squared y in this bottom term. It's not here, it's not there, it's not there. Where could the x squared y be? Well, here's the good news. It could totally be this. Totally fine, right? This is allowed to be any function of x and y. So for the moment, I'm kind of thinking x squared y would be a handy thing to put there. All right, next, there's an xz there. There's an xz there. Conspicuously missing in the middle line. There's no xz that I can see. But again, it totally could be that. No problem. Right? And you can probably guess how this third one's going to go. There's a couple of terms, but missing from the top line, but it could totally be this. And so all together now, as long as I choose these partial constant functions, according to the sort of color coding I've got going here, what is my f? Well, my f is going to be what all three of these things are, namely blue plus orange plus green. Let's see here. So that from the blue, that from the orange, and here it is, that from the green. And everybody wins. Everybody see how that goes? It's a pretty easy game to play. All right. Now, this I should clarify. This is how you find an antigradient. When an antigradient exists, right? This is not going to change the harsh reality of if an antigradient does not exist, this will not somehow make it exist, right? If it doesn't exist, this is not going to work at all. And let's see how that plays out. We already know from a previous example that this vector field right here, right, Green's operator is not 0. This vector field has circulation in it. Circulations can't be gradients, right? Because that's if you have a circulation in a gradient, that means that you have a loop that you can walk where you just keep going uphill all the way around the closed loop. And again, that's nonsense. That's MC-Escher nonsense. Right? So we know there is no antigradient. So how does the game fail? And playing the usual game, I need for my antigradient to equal to both of these things. I'm going to let y'all think through the anti-partials, etc. And now play the game. And can you make this work? And I claim you're going to lose. This is This is tic-tac-toe where you don't get to move first, right? You're going to lose. No way to do it. Does everybody kind of see how this is not going to work out? Okay, so that's it. That's the last of that section. That's the last of section 6.3. That's the last of chapter 6. And we move on now to chapter 7. Sorry. Mm-hmm.
So does C1, C2, C3 form an antigradient?
No, so the antigradient is going to be the thing that all of these are equal to.
Oh, okay. So it's just like the full expression.
Yeah, that's right. So it's not the sum of these, and it's not sort of any one of these. All three of these things have to be made to be equal, and if they are all equal to each other, then f is what that thing is that they're all equal to. Yeah. All right. Okay, so moving along, off to chapter 7. Chapter 7 is going to have a lot of things in common with chapter 6. It's going to be about taking this idea of accumulation theorems, right, and applying it to a new situation that we hadn't previously considered, where, oddly, unexpectedly, we find certain things that are accumulating quantities that we hadn't anticipated. Right? And then writing down the corresponding theorems. In order to make that all work out, though, we do need to develop a new kind of an integral. There's a kind of an integral that is deeply connected to anyway of these big theorems. And in order to talk about this new kind of an integral, we need to talk about how to parameterize surfaces. So thus this first section. Okay, so first of all, what is a parametric surface? I'm going to say it's kind of exactly what you think it is, based on flashing all the way back to first day of class. Here you notice section 1.2, and we talked about a parametric curve, right? And a parametric curve is where you have position as a function of a single parameter. And we like to think of that as being time, but anyway, it doesn't have to be. But anyway, the point is position as a function of one parameter, and then you get a one-dimensional curve. So we're going to kind of do the analogous thing here. We're going to talk about position as a function of two parameters. That's going to give us a two-dimensional thing. And you can see that in action in this example here. In fact, this is a flashback to section 1.5. I think there was a homework exercise that was kind of sort of related to this. But if you want to parameterize a plane, here's a nice way to do it right there. All right, I hope this looks familiar. Just as a reminder, what's going on here is, let's see, if you just kind of look at the various terms, we have a starting point, a given arbitrary point in your plane, and then given a vector v1 defining one of the directions that the plane is parallel to, and a vector v2 defining the other direction. Notice that I can always get anywhere on this plane by going some amount in the v1 direction plus, and then correspondingly, some appropriate amount in the v2 direction. So wherever I might want to be on the plane, I can get there from any arbitrary starting point by just, in some sense, following these two direction vectors, v1 and v2. Everybody happy with that? Does that look familiar? I hope. So what you can see in this example, the reason I like to start with this example is I think it's pretty satisfying. You can see how these parameters are making it that you get a two-dimensional thing. S is what allows you to go as far as you want in this direction, and T is what allows you to go as far as you want in that direction. And if you've got two parameters telling you how you can move sort of in different directions from each other, that's going to give you a two-dimensional result. So I hope that seems plausible, believable. Everybody okay with that? All right. Okay, let's see some more examples. Real quick though, sorry, I got ahead of myself. Because you have two parameters, they can't both be time. I mean, I would totally watch that sci-fi movie, but it's not a real thing, right? And so you have to kind of concede here that they're just parameters again at this point, and so you have to kind of bail on the whole time metaphor. But that said, asterisk, we are going to, in a few minutes, think about a different point of view on this where we'll kind of sort of maybe a little bit sort of recover that time perspective. But anyway, that's foreshadowing. Okay. All right, so another example. Y'all will recall graph parameterizations. The big idea was whatever your input variables, whatever your input variable, singular, is, let that be your parameter. Here we have two parameters. Whatever your input variables, plural, are, let those be your parameters, plural. It's kind of a ripoff of this old idea. And I claim this works really well. It's everything will just fall into place if you just follow this simple rule. If you are looking at a graph, which you'll notice this is, right? If you're looking at a graph, then again, whatever are your input variables, let those be your parameters. So let's see how this flies in a particular example here. We're looking at this equation right here. Notice it is indeed written as a graph. So what are my input variables? My input variables are x and y. So I'm going to let x and y be s and t. And you can explicitly see me doing that right here. X and y are s and t. and I claim it's all over. We've already won. Because you take these formulas for S and T, you plug them into our initial equation, which gives z as a function of x and y, but x and y are now s and t, and that explicitly then gives us z as a function of s and t. And now we have a parameterization. It has just straight up worked. We have position as a function of two parameters, s and t. Lovely trick. Absolutely my favorite way to parameterize surfaces, right? If you had to pick one, this is pretty great, and very adaptable too. Notice it doesn't have to be z as a function of x and y, right? What if you have y as a function of x and z? No problem, no problem at all. Again, just whatever are your input variables, let those be your parameters. So nice example here. Let's look at this equation. What I like about this example, it's not even given as a graph, right? This is just given as an equation. And then you have to take it upon yourself to take the initiative. Hey, I wonder if I can make this into if I could rewrite this as a graph, then I get to use the graph parameterization that works so well. Do notice a couple of crash and burns. If you try to solve for z so that you can view z as a function of x and y, it just doesn't work. You just algebraically cannot solve for z. This equation is not you can't do it. Right? Likewise, you can't solve for x. Right? So there is only one variable in this equation that you can solve for, and that is y. And conveniently, it's not even that much trouble. There you go. Totally solved for y. Now we have, as required, we have y as a function of the other variables. This is a graph. My input variables are x and z. I'm going to let those be s and t. And again, it's all over. Because having chosen x to be s and z to be t, that forces y to be that. And victory, we have position as a weird function of two parameters, s and t. Everybody happy? Okay. All right. Now, there is a version of this, kind of, sort of, depending on how you look at it, in other coordinate systems. Sort of equally convenient. The big trick here is step one, just write down your coordinate system conversion formulas. Here I have the spherical to rectangular conversion formulas written down in vector form. And notice that again, if you have a graph, now this is a spherical graph. I haven't solved for x, y, or z, but I've solved for, instead of a rectangular variable, I have a spherical variable given as a function of the others. And again, it's kind of all over. It's all over. All I have to do is take this formula for rho and plug it in where I see rho in these conversion formulas. Right? And again, inadvertent victory. We have position as a function of two parameters. Now in this case, because of just the specifics of the setup, those two parameters are no longer called s and t. Here they're called phi and theta. If you want, you can go through and make phi s, make theta t. It's fine if you want to. There's no need, though, because all you really need is for these input parameters not to be x, y, and z. Right? You just need to avoid confusing variables. So if you want to call them s and t, go ahead. Might as well just leave them as phi and theta. Everybody doing okay? Pretty cool trick. So this is what I call a spherical graph parameterization, because the spherical part is obvious, right? And graph, because the foot in the door is the fact that my surface is a spherical graph. One of these spherical variables is a function of the others. Okay. All right. Now, that's that's our sort of most convenient, easy method for parameterizing a surface. I do want to show you a couple other cool tricks. It would be nice if every surface we needed to parameterize, we could parameterize with that one convenient trick, but it's just not so. So you may recall long ago we were talking about how you can use vector addition to parameterize thing, and our example that we talked through was a bicycle wheel with a reflector on it, and y'all remember as the bicycle kind of rolls down the street, that reflector does this weird kind of jumpy, bumpy thing, right? And we parameterize that curve by realizing that motion as being a sum of two much simpler vectors. Right, so we're going to do the same thing here. It's just that now instead of parameterizing a curve, we're going to parameterize a surface. This is a weird example, totally. But this method works very well. Okay, so here's what we start with. We start with this surface here called S. It's a portion of an upside-down paraboloid. Nice and simple, nothing to it. But the weird thing is that at every point on this surface, there are hairs of length 1. I mean, just imagine that somebody's got hair poking straight out of their head, right? All the hairs have the same length 1, and they're all perpendicular to the person's head, right? And those hairs, in sticking out like that from this green surface, will make a different surface here that's formed by the ends of those hairs. And that's going to be our goal. How do we parameterize this dark blue surface? Does everybody see the question? Okay, so the big strategy on this is actually not so deep. The big strategy is, let me just get rid of the mess, is to say, all right, well, step 1, I need to find a formula for an arbitrary point on the surface S. Step 2, I need to find a formula for this vector representing a hair coming out of the surface at that point. Right? And, well, a point on my target surface is just going to be green plus orange. That's the big strategy. Does that seem like everybody see the how that kind of is going to work? We do still have to figure out the formula for the green point, and we have to figure out the formula for the orange vector. Okay, well, the green point, it's pretty straightforward. The green point, again, it's a point on a surface which is a graph. Graph parameterization tells me that is just this trick right here. Straight up graph parameterization from the given equation for the surfaces. Everybody all right? Okay, cool. Now, next part of the question, though, what are we going to do about these normal vectors? How am I going to figure out how to find such a normal vector? Keep in mind what the characterizing feature of this vector is that it needs to be perpendicular to this surface S. I need to find a vector perpendicular to a surface. What tricks do we know? Let's rummage through our toolbox. What do we know about how to find a vector perpendicular to a surface? Oh, gradients are perpendicular level sets, right? So if we can make that work, if we can kind of fit this scenario into the idea that gradients are perpendicular to level sets, that would be great. And that's actually pretty easy to do because even though our original surface here is given as a graph, I can move terms around, right? And not too hard to rewrite this as being a level set of that function there. This is our surface S is where this expression is equal to 0. Is that cool? So forget about this graph business. I don't need the graph business anymore. It's done its duty, right? I've used the graph parameterization. Thank you. Goodbye. This surface now I'm going to think of as being a level set. And when you have something as a level set, you want to find a vector perpendicular to it. Cool. A vector perpendicular is just the gradient of the function whose level set you're looking at. What do you think? Everybody okay? Now, of course, this gradient is arbitrary. It's going to have random length, right? We don't want the vector of random length. What we want is a hair of length 1, right? So I'm going to normalize then. It's just making it look more red. Oh, man. Let me just do this. I want to find a vector of length 1 that points in that same direction. So divide this gradient by its own magnitude. And boom, there we go. So it's all over but the shouting at this point. Let's go ahead and do that. We have a formula for position on S as a function of our two parameters. We have a formula now for our hair normal vector as a function of those same two parameters. And altogether, then what we want, points on the surface H, are going to be just green plus orange. Everybody good? Kind of a weird example, but it's a nice example of this idea of taking something hard to understand and representing it as a sum of things that are, in their own different ways, relatively easy to understand. And it's also a nice example of how you have to kind of remember stuff from long ago, such as this business about gradients. Okay, moving along. Here's a tricky one. Very powerful, though. Really useful. Suppose I wanted to parameterize this donut. And as a surface, whatever reason, maybe I want to parameterize. Maybe I want to keep track of how much glaze I'm putting on the surface of the donut. I don't know, something like that. Okay, well, how are we going to do that? There are multiple ways to do this, I'll point out. But what I think is a really natural and simple one is this idea of create a coordinate system. Really simple way to think about it. Forget about parameterizing just for a moment. Just pretend that this is a world that you're living on. Pretend like this is the strangest shaped planet you've ever seen. Imagine if you were building a civilization on this planet. How would you describe location? What would be the longitude and latitude concepts that you would use on this planet? Right? Any way that you can set up a coordinate system for this scenario. And so I propose, I think it's a reasonable choice, it would be that we would talk about first, wherever your point is, how far around do you have to rotate from the xz plane, the positive x portion of the xz plane, to get to that point. Right? We're going to call that angle S. And then that point that gets you to that, I think would be reasonable to talk about how much do you have to go up from what you might call the equator to get to there. We'll call that T. Does that seem reasonable? Now, in this case, frankly, they're kind of like longitude and latitude, right? S is kind of like longitude, sort of. T is vaguely, kind of in a way, kind of like latitude. In this case, the coordinate system is highly recognizable. It won't always be that way. You don't have to always think about literally longitude and latitude, but whatever your surface is, just think what would be the natural way to describe where you are on that thing. Okay. With that established, we're going to let those be our parameters. S and T are going to be our parameters. And now I just literally have to compute the coordinates of that point. Okay. All right. Now, there's some specifics in here, details. Please don't get lost in the details. The details matter, sure, right? But and you do want to go through and make sure that you understand all those details. But the big picture is really the point here. So the big picture idea is that I can first identify this point in the XZ plane, the thing that's going to rotate in to the point that I actually want. And then the next thing I'm going to have to do is figure out how to rotate this light blue point to identify the dark blue point. Okay? So let's take them one little bit at a time. Let's start with just the light blue point here. Keep in mind, by the way, I'm given certain of the dimensions of this donut, right? What you might call the larger radius is a value A, and what you might call the handle radius or the smaller radius is going to be some value B. So with those numbers being given, I can just look at this picture here, and that point is going to be specifically, let's see here, color choices. It's going to be that, I'm sorry, I wanted this in pencil mode. It's going to be that vector right there, which is just a constant. That's A, 0, 0. Plus this vector right here, and that you can imagine as you sort of as this angle T increases, that's going to kind of just go around a circle. So that green vector is just going to be kind of sines and cosines. Does that make sense to everybody? Now again, details. Make sure to think through those details. Here we go. Good exercise to make sure you think through those details. Here's the answer, by the way. That's that A vector. And this is that B vector. And therefore, altogether, the point that we're actually interested in is that, which simplifies to that. Everybody see the big idea there? It's another one of these, sometimes vectors are much more easily understood as sums of simpler vectors. Nice trick. Okay, next thing, we're going to have to figure out how to rotate that thing around, right? We've got this light blue point P. We know that. How are we going to do a rotation? Specifically, a rotation by an angle S. Even more specifically, a rotation by an angle S around the z-axis. And again, the geometry of the scenario that we're dealing with tells you these details. Right? I'm going around the z-axis because, well, picture. So, good news. This is kind of the easy part. We have a formula for how to do rotations. Right? Rotations are linear transformations. Linear transformations are represented by matrices. Matrices can be understood by their columns, and the columns are the images of the standard basis vectors. So again, flashbacks to Math219. Again, reminder: make sure you're really good with that kind of stuff. We're going to assume that you're proficient with how to write down matrices representing geometric linear transformations like this. So details for y'all to check for yourselves, and with that matrix in hand, we are in business. Let's see here. Let me kind of get rid of all of that. Hang on. Here we are. So we have our formula for our P vector. That's that. We have our formula for our R matrix. Right there. The point that we're interested in, right, we're trying to describe this arbitrary point X, and it is just what you get when you take that light blue point and rotate it per the purple. And now you just have to multiply out this matrix vector product, and again, a little tedium, a little stuff to be written down, and there you go. Ready with me? Yeah.
Does anything change if you have like another vector that's just rotating around the circle that you add vector p2 instead of like making it like a rotation transformation as a function of s?
I guess I'm not understanding. Say again.
If you had like another vector that was parameterized by x,
So,
that just rotated with radius a.
Okay, so it's like a different p.
Yeah.
Okay. Well, maybe let me ask. Maybe you mean this. Are you describing perhaps like a different choice of coordinates? In other words, if I didn't describe this point by way of this angle, but maybe I described it by way of an angle measured from the top of the donut or something like that. Yeah, that would just give you a different parameterization, but it totally still works.
Oh.
Yeah. So how I set up these coordinates is, in other words, highly arbitrary. I made these choices just because they're kind of familiar, right? I like to think of the equator kind of on the outside of the donut, and that's where I arbitrarily indicated t would be 0 there. But yeah, totally arbitrary. You don't have to do that. Yeah. Anybody else? Okay. So again, really useful trick. The big picture, and again, it's easy to get lost in the details and the trig and the linear algebra, blah, blah, blah. But the big point here is when you have a surface, consider whether you might have a very natural sort of coordinate system on the surface that you can kind of think in terms of, and then there's just a kind of a resulting geometry problem to turn that into a parameterization. Okay. All right. Last method I'm going to show y'all. And that's deforming an existing parameterization. So sometimes the thing that you want to parameterize looks a lot like something that you already know how to parameterize. So, for example, we already know how to parameterize the unit sphere. Right? The unit sphere, easy to parameterize because it's a spherical graph. Rho equals 1. And sure, you can think of it with this algebra, this rectangular equation, I suppose, right? But from the point of view of it being a spherical graph, we write down the spherical graph parameterization from a couple pages back. Parameterization, and then of course now if you want to separate that into 3 coordinate equations instead of 1 vector equation, whatever. Not a huge distinction. Everybody good? Okay, so now, but what we want instead now instead of that equation, suppose now that I want to parameterize this ellipsoid that has a significantly different equation. How can do I have to start over from nothing, right? Do I have to, forget about all that green stuff. It's not the same as the blue equation, so I got to start all over. And not really. So what you'll notice, of course, now there's we've already talked about the following. When you turn one equation into another by doing a sort of a replacement, everywhere you see an x, you replace that with x over a. That flashbacks to chapter 2, right? We were talking about these kinds of deformations. We know what that does. Right? That stretches in the x direction by a factor of a. Yeah? Anybody? Okay. Okay. Well, so how am I going to recognize that in the parameterization? You've got 2 different ways that you could proceed. The most immediate and I suppose obvious thing to do is just recognize this green parameterization up here is, again, it's equations. If you want to do the same thing to these equations that we just did to these equations, go ahead, right? For example, I can take this x here and literally replace it by x over a. Totally fine. That will do the exact same stretching. Here's a different way to think about it. Perfectly reasonable alternative, and that is to say, I know that what this deformation does is to stretch by a factor of a in the x direction. I know that my x coordinates are literally then going to be increased by a factor of a So go ahead. Right, and here it is. You'll recognize our green parameterization kind of here. And if I want to make the x coordinate a times as big, there it is. Okay, I just made it a times as big. Right, this up here, the first entry in this, that is literally my x coordinate, and multiplying it by a just directly makes it by a factor of a bigger. So that's your other option. Either one of these, take your pick, results in a perfectly good parameterization for your ellipsoid. In fact, they result in the same parameterization for your ellipsoid. You'll notice that if x is equal to a sine phi cosine theta, that's the same as x over a equaling to sine phi cosine theta. Just take the a here and move it to the other side of the equation. It's the exact same result. So two different perspectives on the same idea. How we doing? Is everybody all right with that? So you've got several methods now for how to parameterize surfaces. Neither one of these is sufficient. The collection of all of them, also not sufficient. Right? This is not an exhaustive collection of methods, but they are sufficient for what you're going to see, at least in this course. Parameterizing is something that sometimes you have to get creative with. Okay. Last thing I want to point out, there are several examples in the whoops. Oh, come on, not already. Again with the thing dying. Oh, man. Okay. Sorry about that. Let me switch to the other one here. The book does give many more examples. I have a little bit of a complaint about the examples that are in the book, though. They kind of go what I'm going to call the wrong direction. In practice, what y'all are going to need when you're out there doing stuff, right, applying multivariable calculus in context, you're very often not going to be starting with a parameterization and then trying to figure out what it is. It's going to be the other way around. You're going to be given surfaces described in some way, and you're going to need to create parameterizations. Now, you'll notice that all the examples that I've showed you fall into this latter category. We have here a surface described in some way, and I had to create the parameterization. Likewise here, we created the parameterization of a surface described in a different way, right? Etc. With all these examples I've showed you, we've created parameterizations. All of the book's examples, most, maybe not all, but anyway, certainly most of the examples in the book assume you have a parameterization. And then they just investigate, okay, what is this thing? What is this parameterization that we already have? So anyway, worth looking at, but just do keep in mind creating parameterizations is kind of the real-world version of the problem. Okay, so I'm going to make a couple of observations about parameterizations. A couple of, we're going to just kind of go down a couple of rows here, see what happens. Here's a parameterization. Position as a function of two variables. Modest observation, if I were to fix one of these parameters, right, I started off with position as a function of two parameters, but if one of them is fixed, it's not really a parameter anymore, right? If I nail that down to t is not allowed to change, t is now a constant. Call it k if you want to make you feel better, right? But it's just totally a constant. Now I have position as a function of one parameter, and that's what a curve is. Right? So this is called the S-coordinate curve. The S-coordinate curve is what you get when you fix t and view the position then as a function of only the one remaining unfixed parameter. Reasonable idea? All right, so let's see an example of this. Here is our spherical graph parameterization for the sphere. Right. Position is a function of two parameters, phi and theta. Okay. I am going to now fix one of them. Let's start by thinking about fixing. Let's see here. Let's fix theta first. So we're going to fix theta. We're going to fix theta to be pi over 4. So theta is not allowed to change anymore. Theta is now stuck at pi over 4. Note that means that we are stuck on this plane here, where theta is equal to pi over 4. Let's see, our position is now a function of just one actual remaining variable. Phi is our only remaining variable. Phi, as it moves, will kind of make us do sort of like that. Right. Low values of phi have me up here. High values of phi have me going further down. And again, that gives me a curve. This is called the phi coordinate curve, because phi is the variable. Right, all right? Okay. Now you can see that over here on this other, on the left side, if you will. You can see, again, I've taken theta, and it is fixed at pi over 4, so we're stuck on this line, where where theta is pi over 4, and now phi being allowed to change as phi goes along that line. Phi goes from 0 to pi over 6 and then beyond. We're tracing out, in some sense, a straight line, horizontal straight line there in phi theta world, and that's taking us down, which you might call a meridian, right, on this sphere. Okay. All right. Likewise for the other direction. Let's see here. How are we doing on time? We have okay. Let's just go ahead and finish this example. What happens if we fix phi now? I'm going to fix phi at pi over 6. Phi is not allowed to change. What does it look like if phi is stuck at pi over 6? Well, a constant value of phi is going to give us kind of a cone-shaped thing. We're now stuck on that cone, and as theta moves, right, as we move exactly in the theta direction, from less than and then to pi over 4 and then to greater than pi over 4, well, that's just going to move us around latitude line, you might say. Like that. Right. This is called a theta coordinate curve. Okay. All right. So we're only going to have a couple of minutes left for this next thought. We'll probably have to do this again next time. But I want to plant a thought for y'all. See if I can get this to all fit. And this is what we have down here, this one observation here. Partial derivatives of your parametric surface, I claim, are velocities of your coordinate curves. It's ultimately, it's not immediately obvious when you glance at the way it's written down there, but if you just kind of think through what exactly is a partial derivative and what is a velocity of a coordinate curve, they're just literally the same thing. Let's kind of walk through it. What does it mean if I wanted to take the, let's say, the S partial of this parametric surface right there? The S partial would say that I'm going to let t be a constant, and then I'm going to take the derivative with respect to S. That's what a partial derivative of that parametric surface would be, right? You set the other variable equal to a constant, take a derivative with respect to the remaining. Okay. Now, by comparison, what is a velocity of a coordinate curve? Well, wait a second. A coordinate curve, to be a coordinate curve, the first thing you have to do is, let's see here. Being a coordinate curve, you have to fix one of the variables. So we're going to fix t now so that we have, in fact, a coordinate curve. This is a coordinate curve because a position is now a function of one parameter. And how do we take the velocity of what we now recognize as being a parametric curve? Velocity means take the derivative with respect to the parameter. And so again, just literally taking the derivative with respect to s. So both of these things are saying fix one of the parameters, take the derivative with respect to the other. So they're the same. And we'll pick up there next time. This is a good stopping point. Y'all have a good rest of your Wednesday. See you on Friday.